Hello everyone, I'm Rajasri and I'm working as Assistant Professor in Department of EEE at MLR Institute of Technology, Hyderabad, and today's my topic is MOSFET. MOSFET, it is abbreviated as Metal Oxide Semiconductor Field Effect Transistor, and in this particular lecture, we will be completely seeing about MOSFET, its symbol, structure, as well as input and output characteristics of MOSFET. And here, if you see, this is a symbol of MOSFET. We have both N-channel, there are two types of MOSFET basically, that is enhancement MOSFET as well as depletion MOSFET. But most probably we'll be making use of enhancement MOSFET itself, and this is most popularly used even when compared to that of the depletion MOSFET, and each is further classified into N-channel MOSFET and P-channel MOSFET. And if you see in these both, N-channel is preferred due to the higher mobility of electrons. N-channel is mostly preferred even when compared to that of the P-channel, that is because of the higher mobility of electrons which is found in the N-channel MOSFETs. So here there is the structure of normal MOSFET, and even before going to the structure, let us see the symbol in detail. This particular MOSFET, it consists of drain, source as well as gate terminals. MOSFET is a 3-terminal device which has got drain, source as well as gate terminals, whereas if you see BJT, it has got base, emitter, collector. So here arrow direction indicates the direction of current flow, and here in P channel this is the direction of current flow. And here if you see this particular MOSFET, there is nothing but it is a voltage control device. It is a voltage control device. Current flow is mostly due to the gate to source voltage. The output current, drain current can be controlled by making use of this particular gate to source voltage. So that is the only reason that we call it as voltage control device. And here MOSFET, it is a unipolar device, whereas BJT, it was bipolar device, whereas here this particular MOSFET is a unipolar device because the conduction of the current flow is due to the majority charge carriers. So that is the reason this is a unipolar device. And if you see, this is nothing but the structure of the BJT, and here it has got gate to source voltage. Here let us consider VGS is equal to 0. The gate source voltage initially we are considering it as 0. When VGS is equal to 0, in that case, if you apply the voltage, see, negative is applied to the when gate source voltage is 0, and when VDD, that is drain to source voltage, is applied, in that case this negative is connected to the N layer and positive terminal is connected to the N layer. And because negative is connected to N layer, this we call it as forward bias mode. And here, since positive is connected to the N layer, this comes under reverse bias mode. In that case, one of the region is reverse bias, hence it doesn't conduct any current. And let us interchange the terminals. Say this is positive and for now this is negative. And if positive is connected to N layer, in that case this comes under reverse bias mode. And if negative is connected to the N layer, this comes under forward biased mode. Even in this case, one of the region is reverse bias, there is no conduction of current. That is, when the gate to source voltage is made 0, and even if drain to source voltage is applied, in that case device does not conduct any current through it. So this is the structure of a normal MOSFET. And if you see the another case where here we have applied this particular gate to source voltage of say 2 volts, gate to source voltage of 2 volts. In that case, if you see, there is a metal oxide layer which acts as a capacitor, And here, when gate to source voltage is applied, in that case, the positive ions will be accumulated at the upper plate of this particular metal oxide. Similarly, negative electrons will be accumulated in this particular region. And because of this, mobility of electrons will be taking place in this direction. Mobility of electrons will be taking place in this direction, and since electron flow is in this direction, always current flow in the opposite direction to that of the movement of the electrons. So that is the reason current is flowing in this direction in the device. And now what we do is, let me further increase this particular gate to source voltage to about 5 volts. In that case, what happens? The number of electrons accumulation gets increased in this region, and because of which further electron movement gets increased. And if electrons, as I told you, if electrons is moving in this direction, the current flow will be in the opposite to that of the electron flow, and that is the reason now current is flowing in this direction. So ultimately, a current is flowing from drain terminal to that of the source terminal in this direction. So this is all about the normal BJT, and if you see the characteristics of a power BJT, it has got high input impedance of about 10 to the power of 9 mega ohms. And now it has got small leakage current. The leakage current of this particular MOSFET will be very small, and it will be in the range of nanoamperes, and it has got no secondary breakdown problem where it was being observed in the BJT, and here in MOSFET there is no as such secondary breakdown problem at all. And this can be operated in low power and high frequency applications. This can be operated in low power and high frequency applications. And the voltage rating of MOSFET is about 500 volts, and current rating is about 140 amperes. Whereas BJT, it was operated with the voltage rating of about 1200 volts and 800 amperes. Whereas here this is operated at 500 volts, 140 amperes. And then let us see the structure of power MOSFET. So here there is the normal MOSFET which is being considered, and this is the structure of power MOSFET. And if you see, this particular normal MOSFET has got only 2 layers, that is P-type, and this N plus substrate is embedded over P-type layer. Whereas here there are additional layers, even when additional layers which are added when compared to that of the normal MOSFET. So here in this particular power MOSFET, the bottommost layer is nothing but N plus substrate, and which is given as the doping level of this particular N plus substrate is given as 10 to the power of 19 per centimeter cube. And above which there is N minus layer. I said N plus is the doping level is very high, and if it is mentioned as N minus, in that case the doping level is less, and the doping level of this particular N minus drift layer is given by 10 to the power of 14 per centimeter cube. So this drift region, it determines the breakdown voltage of the device, and which is very important, and this is an additional layer to that of the normal MOSFET. And above which there is a P-type body, and into which N minus substrate is being added. And here the thickness of this particular N plus substrate is 10 to the power of 19 per centimeter cube, which is heavily doped, and the P-type body is moderately doped, and it is of about 10 to the power of 16 per centimeter cube. And here let me consider the gate terminal, and I am applying the drain to source voltage. So initially, if you see, here there is only one MOSFET, and here if you see, this is one of the MOSFET, and even this is looking like another MOSFET. This is because in power MOSFET, in order to meet the high power rating capability, here number of MOSFETs are connected in parallel such that the current rating of this particular MOSFET can be increased. So that is the reason number of MOSFETs can be connected in parallel, and here we are showing only two MOSFETs. This is one of the MOSFET and this is another MOSFET which is connected in parallel just to increase the current rating. So here when the gate is connected, gate voltage will be applied. When the gate voltage is actually applied, in that case, see, the similar metal oxide layer is present even here. When the gate voltage is applied, at that instant, the positive ions will be accumulated in the upper plate of that of the metal oxide, and then negative electrons will be appeared across this region under the lower plate of that of the metal oxide, which is acting as a capacitor. See, this particular N minus region around which the electrons are being accumulated, and because of which since gate drain to source voltage is also applied, VDS is also applied, in that case the current starts flowing in this direction. That is from drain to source. In MOSFET, always current starts flowing from drain to source. Whereas here, if you observe, here N layer is actually connected to the negative terminal and positive terminal is connected. So obviously P type will be connected to the positive terminal. So in that case, when N is connected to negative, this is forward biased and this is reverse biased junction. So because of which current will be flowing only through this particular forward bias region. So that is the only reason when the gate to source voltage, sufficient voltage is applied across this particular gate terminal, and when drain to source voltage is also applied, in that case the current will be flowing right from drain to source. Right from drain to source only through the N layer, because N layer is actually forward biased here. And here if you see, current flows from drain to source, and this particular current ID is controlled by making use of gate to source voltage. That is the only reason MOSFET is termed as voltage control device. This is a voltage control device. And see, reverse recovery time of this particular MOSFET is less. So that is the reason this can be applicable comfortably for the high frequency operations. This can be comfortably applied for the high frequency operations. So medium power and for higher frequency operations, we can make use of MOSFET. And if you see, these are the input characteristics and these are the output characteristics of a MOSFET. So we can also call it as transfer characteristics. Transfer characteristics, where output current, that is drain current, is controlled by making use of gate to source voltage. Gate to source voltage. In that case, when the gate to threshold voltage VGT is increased beyond 2 to 3 volts, in that case the reverse bias junction, the depletion layer breaks and it starts conducting. The current starts conducting. This is all about the input characteristics. Coming to the output characteristics of a MOSFET, where output current versus the voltage VGS, gate to source voltage. Whenever the gate to source voltage is 0, in that case device does not conduct and there will be no output current. And if you see, this is nothing but cutoff region, and cutoff region, as I already told you, this will be operating as a off switch and there is no output current except some amount of leakage current will be flowing through the device. And then we have VGS. As we go on increasing this particular VGS, in that case ID will be increasing. See, slowly it is increasing and then it is becoming constant. And in BJT, we had saturation region, where in MOSFET we call it as ohmic region. So this is all about the output characteristics of a MOSFET, and in coming up lecture we will be seeing IGBT.